All right, so next example, we're going to actually find the curve of intersection between the surfaces x squared plus y squared equals 4 and x plus z equals 2. Now, you don't need to have a perfect graph of this in your mind, but you do need to recognize what these basic objects are, what kind of objects they are. This is an equation of a circle in 2 space, so it's a circular cylinder stretched along the z-axis in 3 space. I guess we do it like this. And then this is a plane. So we've got some sort of plane slicing a circle, and so we expect some kind of curve like that, and we're supposed to parameterize it, find the curve of intersection. Really, instead of maybe find, it should be parameterize. That would be a little bit more clear what the instructions are. Okay, so what you're doing is you're looking for equations that capture this curve. And anytime you see a circle, to be honest with you, that's where you want to start. We're going to use polar, and some of you guys expressed a little concern over polar, so let me just tell you right now, anytime you want to work on an equation of radius r, you can just set, let's do this, you can set x equal to the radius times cosine of t, and y equal to the radius times the sine of t. And so that's just from this equation. If I'm going to live on this cylinder, and I'm going to try to parameterize this, x needs to be cosine t, y needs to be 2 cosine t, y needs to be 2 sine t. Now, if you go over here, the fact that I can solve for z is huge. I can say, well, look, this is the same thing as z equals 2 minus x, and so that means z equals 2 minus 2 cosine t, and all of a sudden, I've got my parameterization, and so I can say r of t equals, here we go, 2 cosine t, 2 sine of t, and then 2 minus 2 cosine t. And I do want to limit my t values. Let me slide this down. I only want to go around this curve once, and so I can see, look, I'm on a circle, so all I have to do is let t run between 0 and 2 pi, and that's going to trace this out. So let's switch this thing to Mathematica, and then we're going to come back and keep going in the notebook. All right, let me slide this Mathematica notebook over. Hopefully you can see that. So here's what you get when you graph that cylinder that we talked about, and then the plane. Here's the 2 surfaces that we were asked to parameterize the intersection curve of. So you can kind of see the intersection curve there. I actually went ahead and graphed them a little bit more opaque and asked Mathematica to mark that boundary curve. So that's the space curve we're trying to parameterize. And so we did that. This is what we came up with. And you can tell, looking at this picture and this one, that they should match up, but we don't know where this actually lives in space. I want to glue this picture and this picture together and make sure that it really is lining up on in the same spot. And so when we do that, here I've combined these graphs, and you can actually see how the blue graph and the black boundary are lined up so well that you can hardly see. Mathematically, got some little dots of blue there where they're kind of overlapping, and you can see that we nailed it. We got exactly what we wanted. So that's the Mathematica version of this problem. Let's switch back to the notebook and wrap up. All right, so the next thing that I want to look at with you is the definition of the limit of a vector function, and it's exactly what you think it should be. Given a vector function that looks like this, the limit as t goes to a of r of t. It's just defined component-wise, so it's the vector, and you take the limit as t goes to a of each function. And so you can sort of see calculus 1 happening here, but we're just dragging it up to 3 space by doing 3 of these limits at once. So you thought Calc 1 was fun. Think of how much more fun this is. We can do sort of 3 limits at once and then embed that in a vector, and now we're 3-dimensional. So quick example of this, let's drag this up just for space. Again, you can just look at this and basically take the limit component-wise. So sine t over t, as t goes to 0, this goes to 1, this part goes to 0, this part goes to 0, and so quite literally this is just 2 minus 1 is 1, negative 3 plus 0 is negative 3. Root 4 is just 2. And so that's it. So the limit as t goes to 0 of this function is this. If one of these components doesn't have a limit, the whole thing doesn't have a limit. And that's really important. All right, and then we're going to call r of t continuous at t equals a if the limit as t goes to a of r of t is equal to r of a. And this is almost exactly the same definition for continuity that we saw back in Calc 1. And so basically a space curve is continuous if it's not jumping like this. There's no gaps between it. You can sort of not pick up your magic wand in 3 space as you sketch it out. So let's end this video here, and in the next video we're going to begin taking some derivatives.